Okay, so this is supplemental on computing the closest pair among a set of points in the plane. It's a very nice example of divide and conquer. Somehow there are a lot of such nice examples in computational geometry. And this is supplemental, which probably means that it's not going to be for the exam. So see this recording only if you're interested in the topic. So the problem. We're given a set of points in the plane, and we would like to find the pair of points which are closest to each other while, of course, being distinct. So in this case, it's going to be this pair of points, which was picked especially for this purpose. And the question is, of course, how to compute it efficiently. And now, of course, the naive algorithm is you just go over all possible pairs of points, as in the definition, you compute their distance, and you take the minimum. And then if you want the pair itself, you do arg of this, right? So that would give you the minimum pairs. So the naive algorithms take quadratic time. Okay, and essentially, if we are in really high dimensions, we cannot do better than that. Formally, if you're in d dimensions, and d is really large, the fastest algorithm we really know is dn square. There are minor improvements, but they're probably not practical. So in practice, this is really the algorithm. If you're in really high dimension, this is sometimes called the curse of dimensionality. But in 2 dimensions, you can do much better, and there is as the topic suggests, a nice divide and conquer algorithm for this problem. So the algorithm works as follows. The idea is how we want to divide the points first. And of course, the question is how to divide the points. So the most natural way to divide the points is just split them in the middle according to x or according to y. What do I mean in the middle? Well, you want to pick the median, right? You want to pick you take all the x values of the points, and you pick the points such that half the points have smaller x value, and half the points have bigger x value. So you visually you're splitting the point set into 2 parts by a vertical line. Let's just assume that this vertical line is the y-axis for our purposes here. It would simplify the discussion. Okay. And we're going to have the points left to the y-axis and the points to the right of the y-axis. And those are the 2 parts. Now, and if we are assuming that y-axis, it's just looking on the x-coordinate. Is it smaller than the value or bigger than the value? That's how we split it. And now we recursively assume that we compute the closest pair distance on the left side and the right side, right? And we take the minimum. We take the minimum. L is the minimum distance found on the left side and the right side. Now, of course, this is not quite the right distance because there quite possibly be 2 points that are extremely close to the border, right? Like Kansas City in Mississippi and Kansas. And in fact, they realize the closest distance. So we need to if we want the closest pair distance of all the points, we need to find the bichromatic, the bi-sided distance between points that are on the left side and the right side. But the important thing is that we don't have to worry about points that are far away from the separating line. So we take all the points that are in distance L at most from the left side of the line and all the points in distance at most L on the right side of the line. We get a strip, and we take all the points in this strip, which is the set PM. Okay? And now we want to compute the closest pair distance in the set PM. Right? Formally, what we really want to do is to compute the closest pair distance in PM and take the minimum of this with L, and this would be the closest pair distance of all the points. Right, because either the close point distance is realized by point to the left of the line or point to the right of the line, or by 2 points that, the segment connecting them cross this line. So the question is how to compute this distance. And the claim is that those points that fall into the strip P of M, the middle points, This can be done in n log n time. So let's see the algorithm. And the basic argument that underlines this algorithm is the idea that points have to be nicely behaved. So for example, the configuration here of points is not possible because those 2 points are on the left side and the distance is clearly smaller than L, right? So when we called recursively on the left side, we would have gotten a smaller value of L if this was the case, right? So the points of PM have to kind of be spaced out. They cannot be too dense together. So to capture this intuition, consider a square of side length L by L that lies on the vertical line, on the y-axis, right? And the observation is that the maximum number of points you can have on the left side that are on this line, this number is at most 4, okay? Because if we have more than 4 points inside this square, let's assume like that, then there must be a pair of them that is on the left side and their distance is smaller than L, right? So as such, this square can have at most 4 points. And now we are going to replicate this square on both sides. And I'm going to call this rectangle an elevator, right? And the idea is that you can have at most 4 points on the left side, at most 4 points on the right side. So this, because the same argument applies to the right side of the elevator. So an elevator can contain at most 8 points, right? Now, the key observation is that if we have 2 points on both sides of the border, on different sides of the border that realize the closest distance, then there must be a way to place the elevator such that those 2 points will be inside the elevator. And if those 2 points are inside the elevator, then we can check the distance between them. Okay, so this is a bit hand-wavy. So let's see in more detail what we are doing. What we're going to do, we're going to take the elevator and we're going to start, it's going to start from the top. And then it's going to start going down. And as it goes down, it's going to encounter the point, right? Points, think about the elevator is going down. Points are going to enter the elevator, in the bottom of the elevator as it's moving down, stay in the elevator for a while, and then leave through the ceiling of the elevator. Okay, so, and this process looks like that, right? Every time that a point leaves or enters, the elevator stops and let them leave or enter, right? Now, the critical observation, of course, is that since a point enters the elevator once and leaves the elevator once, there are only 2 endpoints in time where the elevator needs to stop, right? And in fact, if I have the points sorted by the y-axis, then I can compute these two end critical times. I can compute them in, to begin with, I can compute them in n log n time by just computing for every point the 2 critical times and sorting the time. So this would be of n log n. But in fact, if I have already the points sorted by y-axis, I can do it in linear time because when you hit the bottom of the elevator, you get a list of time, which is just the y-coordinate of the points. And when you hit the top, you get another list, which is the same list shifted by the height of the elevator. So you get 2 sorted lists and you need to merge them, and merging 2 sorted lists takes linear time. So in linear time, you can compute the critical times of the elevator. And now what happens is that as the elevator goes down, every point enters the elevator or leaves the elevator, but the elevator never contains more than 8 points, right? So in particular, whenever a point enters the elevator, you compute the distance of this point to all the other points in the elevator. There are at most 8 points, so this is going to take constant time. And you maintain the minimum such distance encountered. And the claim is that the closest pair distance across the line would be computed in this way, right? And the reason is very simple. If you have 2 points across the border and the distance is smaller than L, then their vertical distance between them is smaller than L, and as such, the elevator would sweep over both of them in the same time. At some point in time, they would be both in the elevator, and the distance as such would be considered and entered into the candidate distances. And as such, we will find the closest distance. Okay, so here's how it goes then. The elevator stops here because the point at the top is about to leave. Another point is about to leave. Now a point is about to enter. Now another point enters. Here the point on the right leaves. Now another point leaves at bottom. Another point leaves. And now the elevator contains only one point, and this point leaves. And now the elevator goes down and crashes. Okay, how many times I told you not to crash the elevator? Boom. Bye-bye, elevator. You were useful to us. Okay, so what we conclude is that if the points are sorted, by the y-axis we can do it in linear time, or if we have to sort them, it takes n log n time, but we can compute the closest pair distance for the middle points in n log n time. Okay, and as I said, if they're pre-sorted, in fact, it is linear. We will see how to use it later on. Okay, so now here's the algorithm for the whole point set, right? We, if the number of points is it's a recursive algorithm, divide and conquer. If the number of points is a constant, we just compute it by brute force. We look on over every pairs and find the distance. So this takes constant amount of work. Then we find the median point according to the x-axis. So we can just sort the point and do it in n log n time. I'm not worried about this at this point. And now I split the point into points smaller than median and bigger than the median. So this takes linear time. And now I recursively call on the left side, left points and the right points. So this is two recursive call. This is, I compute the minimum distance L. I compute the middle points. That takes linear time. And now I call on this special algorithm we just described to compute the closest pair distance for the middle point, which takes n log n time. Right? So we get this. Okay. So if you write down the recurrence, you get the following. T of n is equal to 2tn over 2 plus of n log n. Right? So that bounds the running time. The correctness is again easy because either the closest pair distance is in the left side or the right side. If so, the recursive call would compute it, or it's across the line, but then it must be realized by 2 points in the middle set that are crossing the splitting line, and then the special algorithm would find this distance. So that's the correctness. Now let's solve the recurrence. So the solution to recurrence is n log square n, right? Let me write it again. Plus of n log n. And so the easiest way to see why this is the right solution, we know another recurrence, s of n is equal to 2ts of n over 2 plus O of n. You know this recurrence, right? So think about just taking the log n factor and writing it on the side, right? You are going to, if you write it on the side, then you can solve this recurrence, which we already know a solution is n log n. And then you multiply it by log n. So you get n log square n. So this is the easy way to do it. Otherwise, you can do the tree method or induction or whatever. You will get this solution. This is the right solution. Okay, but as I mentioned, one can do better, right? One can do better, and the idea, so the details become a bit messy. And the idea is that you pre-sort the point by the x-axis and by the y-axis. So this takes all of n log n time. This is, you do it in the top. And now what happened is when I send the pointer to the procedure inside, I'm in fact not going to send the point set. I'm going to send two copies of the point set. One is a linked list sorted by the x-axis, the second sorted list by the y-axis. So in the following code, whenever we do an operation on the pointer, we have to do it on the two copies, right? So the first thing is the same. The median now, I can compute in linear time because I have the point sorted in linear time. So that's one benefit. Splitting the points takes linear time. I just have to do it twice, right? One for the point according to the x-axis, one according to the point in the y-axis. Notice, importantly, that I can do the splitting in such a way that preserves the ordering on those two lists. So I get the point set, again, the 2 points set on the left side and the right side. Each one of them, I have 2 lists of them in the right order. So this takes linear time. I call recursively, as before. And now the important thing is that I call on the special procedure, but now I have the point set in the middle. This also takes linear time. The points in the middle are now sorted by, I have them sorted in y, by the order according to the y order, and now this takes orphan time instead of n log n. So if I do that, the recurrence become our favorite recurrence in the world. T of n is equal to 2tn over 2 plus of n. The solution of this recurrence is, of course, n log n, as we all know. And we also have to pay this extra n log n in the beginning of, in the top level, but that, just adds up. It's the same thing. And we got this result. We got that given a set of endpoints in the plane, we can compute the closest pair and the closest pair distance in n log n time using a divide and conquer algorithm. Okay, before I finish, let me mention that one can do better. So Michael Rubin, in his famous paper about randomization, showed that, in fact, one can do better. One can solve this problem in linear time. So first you need randomization. So it's a randomized algorithm, which means that the algorithm is allowed to consult with, a coin, a random coin, or some source of randomness. It's randomness, and the second thing is that it uses the floor function, which, as I mentioned when we spoke about the RAM model, is not necessarily a great thing to do because there are some problems with floor functions and bit packing and so on. But this algorithm doesn't really do bit packing. It just uses the floor function, so it's kind of reasonable. And with those two things, Michael Rubin described an algorithm how to do it linear time, expected linear time. His algorithm was pretty complicated, but it was simplified, and now it's really a beautiful algorithm. If you're interested, you should take 473, where it's being taught sometimes. And that's it. Thank you very much.